everyone, I'm Qiuyu. You can also call me Luca. So Lin has just given you a brief introduction about fluid-driven or fluidic multimatter. And I think in my part, I will go a little more specific to talk about the fluid-driven multimatter in HCI. So yeah, today we have two parts. The first part is about the capabilities of fluid-driven multimatter. And I think there are like 5 dimensions. I'm just trying to take the fluid-driven multimatter as an example here. So maybe some other kind of multimatter can do the same thing or can do even more thing. Yeah, but I just think that, yeah. And for the second part, we will talk about the implementation of a fluid-driven multimatter, depending on how much time will be left. So yeah, the first part is about the capabilities. Yeah, I think after you understand these capabilities, maybe you will have a better sense of what kind of whether this kind of multimatter is a good choice when you want to design a specific scenario or application. And I will go through them like one by one. Yeah, so the first one is about dynamic affordance. Yeah, I think Lin has mentioned affordance as well. Yeah, if you are still not very sure about what affordance is, there is a very basic definition by dictionary. So yeah, So affordance is basically the quality or property of an object that defines its possible use or makes clear how it can or should be used. Yeah, I think the definition of affordance could be slightly different in different domain or context, but this is basically its core meaning. And this figure is like a very straightforward example. Imagine there's a door. If it doesn't have any handle, you will probably intend to push to open it. If there's a handle like this, a spaceship handle thingy, then probably you will want to like pour to open it. So that is the affordance of the door's handle. And speaking of dynamic affordance, yeah, so literally it means the object's affordance can change dynamically to adapt to different tasks, users, or environment. Yeah, I think Lin has shown this example as well. So adapt to different tasks can facilitate the execution of different actions. For example, if you have a actuated screen, soft screen that can change its shape, then maybe if you need to watch a video, it will change something like tablet. And yeah, here's a phone call, then it will change to a mobile phone. And if you want to do some exercise, it will change to a wristband that you can just verify your wrist. And yeah, and here is another example. Yeah, I think Lin showed this too. Yeah, so we will see a strip like this. You probably want to point it like, so for now it's more like a switch for the lamp. And after you point it, it will curl and become a rounded box shape and then light up. So basically, these two examples explain like how an object can change its affordance. Depends on different tasks. And the next type of dynamic affordance is to adapt to different users, or maybe a specific group of users. Imagine you have a pneumatic mouse that can be deflated or inflated. It can change its size a little to fit your hand. And speaking of hand, actually I'm left-handed, and I wonder like how many people in this room is also left-handed. If you are, please raise your left hand. Okay. Yeah, 1, 2, 3. So yeah, yes. Statistically speaking, there should be like 10% of the whole population is left-handed. However, most of the items like nowadays are only designed for right-handed people, right? And it can be really inconvenient to us sometimes. And what we can do is just to get used to it. So how about the project can get used to me instead of I get used to it? For example, you can have a pair of shaders that can change the shape of its handle, like depends on whether you are a left-handed people or right-handed people. Or we can have a game controller that can change its layouts of the button dynamically. Also depends on whether you are left-handed people or right-handed people. So this is about how an object can change its affordance, to adapt to different kinds of users. Okay, the next type of dynamic affordance is about to change its affordance to adapt to different environments. Yeah, please take a look at this video with the question that what kind of information that this shape changing tree want to convey to the users. Yeah, if you have any thoughts, just feel free to speak. And yeah, no worries, no worries. There's no right or wrong. So it's just about how you perceive it. Yeah, anyone? No. Yeah, so I guess it's just the second day we have hosts like in person. Everyone's still a little shy. Yeah. Okay. So when we design this prototype, we designed like 3 states. So wrapped the handle of the cup means means the water is very hot and also the cup is very hot. So there's something like a small finger that grabs the handle and try to prevent you from kicking the cup off the mat. And there is another state like this that the small strip only release the handle, which means the water is cold to drink. And there's a middle stage like this half grab the handle, and it means that the water is warm to drink. So yeah, so basically this is about how can object change its affordance corresponding as the environment change, and to support maybe influence or maybe convey some information to the users. Yeah. So you can see by changing the affordance to the specific interaction context, objects can increase their usefulness, extend their reusability, and meanwhile improve the user experience. So this is the first dimension, dynamic affordance. And for the second dimension is about doing some augmentation, which means you can integrate the fluid-driven matter with the environment, objects, or even the user's body to enhance its function or ability. Yeah, the first type is to augment the environment. So imagine you have a window, like a pneumatic window, that can change its permeability to the light, to the air. Then it will be able to like regulate the room temperature, the brightness of your room, or the airflow. And it can even be some sort of ambient media that can convey information non-invasively, like it can cast some kind of shadow with texture or meaningful patterns encoded. And the second type is to augment the object. So yeah, basically you can try to actuate a lamp to adjust its height automatically, or actuate a door to close or open automatically. And in this way, you can enhance the object's function or improve their interactivity. And the last type is to augment the users. So yeah, it can be some sort of exoskeleton to help you to lift very heavy stuff, or to assist in the reliability of the wounded. Or it can be a prosthesis. For example, nowadays our bones are becoming bigger and bigger, and it could be very hard to operate it with only one hand. So imagine you have a actual thumb, then you will be able to like zoom the picture with only one hand. Or if the prosthesis thumb is longer enough, then you will be able to press the annoying button in the top left corner of your phone. And yeah, you can also use it to maybe hold an object when you try to operate on it. So this is about augmentation to augment the environment, objects, or users. And okay, this is the third dimension about to present some objects. So the first one is to materialize virtual objects. I'm not sure whether I choose the right word, but what I want to say is that you can bring the virtual object in your screen or in your VR game to the real world. Yeah, in this example, when the user scan encounters a virtual object, a airbag with unbroken shape will like inflate and be ready for its rest. And when the object is no longer in play, the airbag will just deflate and disappear. So in this way, it will make the virtual object like feel even more real to the users, and it will be easier for the users to operate such a virtual object. And this is another example of materialized virtual objects. Well, to be more specific, it's like to materialize the virtual environment around the users. Yeah, and I think this application is like very clever because both Minecraft and the systems they built are all based on cubes. And as you can see, when the user tries to create a virtual cubic block in the virtual world, there will be something like a real cubic pump up in the physical world. And vice versa, when the user wants to destroy a block in the virtual world, and the physical block will disappear. So yeah. So the second type is to reproduce some object existing in the real world. Yeah. So you can, as you can see, the fluid-driven multimeter can have very dramatic volume changes when inflated. But which I mean it can morph from a very thin 2D plane to a very big 3D solid object. And compared to 3D printing, obviously it's more efficient and consume more time. So it can be used for rapid manufacture. And in addition, by controlling the deformation sequence, we can also achieve something like 4D fabrication. Yeah. So this is an example of a reversible 4D fabrication. So basically, all the actuation chamber are the same, but with the channel that connecting all the chambers are special designed to make sure the chambers filled with water in a like different sequence. So in that way, the flower will either fold like one by one or group by group. So it will be like a rose flower or lily flower. Yeah. Okay, so the next type is to expose some objects to human. I like to expose objects that human could not normally understand. Usually some objects are in really macro scale or in really micro scale, and it can be very hard for humans to perceive, to understand it. Yeah, but fluid-driven multimeter may like demonstrate them very well. And in this example, yeah, we created a prototype that can change its weight by pumping liquid metal, and it can change its volume by pumping air. And the users can hold this device and like feel and compare the mass and the size of each planet, in a tangible way. Okay, so this is about to present some objects. And I think this is the fourth dimension. Yeah, so you can leverage some actuating or sensing abilities of fluid multimeter to design some novel I/O devices. And by I/O, I mean input or output. And the subject here is the users, like what kind of output the users can perceive and what kind of input the user can perform. So this example has a beautiful display as a diverter flowing the channel, and it's actuated purely mechanically, which means it will respond directly to mechanical inputs from the users, such as pressing, folding, bending, and there's no computational or electrical components embedded. And it can also be used to provide some haptic feedback. Yeah, in the first example, I was trying to render some very high resolution texture. So it can provide some haptic sensation on your fingertip. And according to the video, Meta released last year of 2017, both feedback haptic React gloves. So yeah, according to them, their gloves can stimulate haptic feedback to the whole palm. And the last example is a jacket that can create some haptic feedback on your body. So like when you have a snow fight in a VR game, you can literally feel the snowballs hit on you. Or you can render some like haptic sensation like a snake wrap around you. As you can see, the fluid multimeter can render haptic on various scale, like from fingertip, body, and the pixel resolution can range from 1 square millimeter to like 10,000 square millimeter. Yeah, and I think we need to show this example as well. So yeah, I think this is a very good example that demonstrates how fluid-driven multimeter will couple the digital world and physical world. So when you edit the digital shadow on the screen, the building will change its state correspondingly, as unshifted output to the users. And the physical model of the building have some kind of soft sensing circuit embedded. So if the users manipulate the physical model of the building, the shadow can change as well. Okay, lastly, yeah, when you try to manipulate the inflated object, actually the inside air pressure will fluctuate. And the leveraging this, you can try to translate the user's operation on the object to some kind of signal that the computer can understand, like with the help of air pressure sensor. And in this paper, they designed a series of different input widgets, enabled by detecting air pressure change. I think we're running out of time. Yeah. So the last one, here's the last one. The last one is about to just for some purely economic or aesthetic purpose, like changing cloud architecture or some kind of fireworks. So maybe they don't have some functional goals. Yeah, but typically they can increase the pleasure or enjoyment of the users. And yeah, to be more practical, you can imagine it to be a toy or some kind of decorations in your house. Yeah, so this is the capabilities of fluid multimeter. Yeah, I hope it's inspiring. And I will cover the second session in the coming weeks.